Hi everyone, can you hear me? Just nod, yeah, cool. Great, thanks very much for having me today. As Tamara kindly introduced, I'm Sophie and I'm a third year PhD student at Cambridge, and I'm taking us back into the world of ancient tectonics instead of Dan's excellent talk on very modern processes. So here we're going to be zooming back to the Archean approximately 3 billion years ago. So just to give you a bit of a broad overview, today, as we'll all know to some degree, we've got a pretty good understanding of tectonics, such that, as we see on this map where we've plotted global earthquake locations roughly with depth, we generally see rigid lithospheric plates with deformation concentrated at long linear margins and distributed deformations occurring in our continental regions. Overall, we're seeing predictable interactions between plates at plate boundaries, and we can also go some way to reconstruct past plate motions. However, reconstructing this becomes increasingly challenging the further into geological time we travel. The oldest oceanic crust is only 300 million years old, so we're just relying on the rocks present on the continents to reconstruct plate motions further back in time. And as you can see on this compilation of approximately how old rocks are in different areas of the world, the further back in time we go, we get a very restricted rock record. For example, as we go back to the Archean about 2.5 to 4 billion years ago, we have a very limited series of outcrops. These are broadly the areas shown in orange, making it very challenging to build a picture of geodynamic processes on a global scale, and necessitating a really good understanding of what processes may have occurred in each of these regions to build up the best possible global picture of Archean geodynamics. So, to return to our picture of modern tectonics, we want to be able to look at the Archean rock record and assess whether the Earth worked the same in the past as it does today. To do this, we obviously need to have a good understanding of what markers modern tectonic processes leave in the rock record and assess whether these match our observations of Archean regions. Subduction is often used as a marker of modern style tectonics, as the high temperature, low pressure rocks produced in subduction zones, i.e. blue schists and eclogites, are pretty characteristic of these geodynamic environments. The figure here shows a global compilation of rocks that have experienced different types of high pressure metamorphism. The bottom row is the record for blue schists and eclogites, i.e. our subduction zone rocks. We don't observe blue schists and eclogites past around 2 billion years. Observations like these have led people to say that subduction might not have occurred in the past, and thus modern style tectonics may not have operated in the past. There's actually a massive amount of uncertainty regarding when modern tectonics started. This recent figure shows the vast range of start dates people have placed on the onset of modern tectonics. Many of the more recent estimates place this initiation at some point in the Archean. This whole thing implies that prior to the onset of modern tectonics, different non-uniformitarian processes may have been operating. To address this question, we have to look at areas of the world that expose Archean rocks and think about what geodynamic environments may have been responsible for their formation. So, to get into the meat of this talk, Archean outcrops expose different structural levels of the Archean crust. There's a broad split in Archean outcrops between those thought to represent the upper crust, you might have heard these referred to as granite-greenstone belts, and those representing the mid to lower crust, which are generally a lot more homogeneous than our upper-crustal blocks, and are mainly composed of rocks that people who work in this area call catchily tonolitic tronschmitic granodiorites, or TTGs, but these are basically just sodium-rich granites. While we don't see high-pressure, low-temperature blue schists or eclogites in Archean rocks, which would provide clear evidence of modern subduction-style processes, we do see rocks in most Archean areas that have been interpreted as moving from the surface or a shallower structural level to depth. The presence of these rocks suggests some process has juxtaposed shallower and deeper rocks. This figure here shows some of the ways these juxtapositions could be generated, ranging from uniformitarian subduction on the right to non-uniformitarian sagduction on the left. Sagduction is the process I'm specifically interested in, and it's been widely discussed as a way to move shallow rocks to depth by the shallow rocks sagging into the lower crust through a density instability. In this study, we're going to develop a numerical model of Sagduction based on density-driven settling and use a test case from Northwest Scotland to show how the model can be used to constrain Sagduction viability in a specific region. In this talk, I'm first going to go through the info I get from fieldwork, petrology, and phase equilibria modelling conducted on those rocks from Northwest Scotland. And then I'll show how I use that information in a numerical model to work out whether Sagduction scenarios are feasible. So just to give you a quick overview of Archean rocks in the UK. The UK's oldest rocks are in Northwest Scotland and are about 3 billion years old. All of the blue rocks on the left-hand figure are where Archean rocks outcrop in the UK, and this area is often referred to as the Lewisian. The rocks in this region that reach the highest pressure temperature conditions, known as granulite facies, with temperatures in excess of about 750 degrees, are thought to represent the lowest crustal level. These rocks are on mainland Scotland in the highlighted box, and we zoom in on this region in the figure on the right. This region of the Lewisian is relatively uniform and mainly comprised of TTGs, that's our granite-like rocks, in dark blue. The TTGs do contain occasional outcrops of other lithologies. These are highlighted on the map and are what people have interpreted as possible shallower assemblages that have been moved to depth. These lithologies are called brown gneiss, mafic gneiss, and ultramafic gneiss, which I'll just give you a quick overview of. So these figures here are typical outcrops of these 4 key lithologies across that whole central region of interest. In general, our darker rocks are higher density as they contain higher proportions of dense minerals. Just to give you a rough idea of mineralogy, I'll flash up some thin section images. So our TTGs are our background. This is our granite-like rocks. They're light coloured and they mainly contain quartz and feldspar with minor amounts of some more mafic minerals. Our brown gneiss contains some garnet and some biotite, still quite a lot of quartz and feldspar. And then as we move into our mafic gneiss, we're mainly seeing garnet and pyroxene, still a little bit of feldspar. And then as we move into our ultramafic gneiss, we're basically just seeing olivine and pyroxene. So what am I actually going to try to do with these rocks? The aim here is to get input information from direct observations of these rocks to constrain our numerical model of Sagduction, which I've just shown schematically here. I'll return to this model in more detail later, but briefly, we're thinking about a dense body detaching from a dense upper layer and sinking through a lower density layer. The low density layer is our TTG granite-like rocks, and the high density layer is made of some combination of our other lithologies. I'm going to quickly take you through the petrology and phase equilibria modelling we carried out to constrain some aspects of this model. Specifically, what were the peak metamorphic conditions, i.e. temperature and pressure, reached during metamorphism? And what was the density and mineralogy of all 4 lithologies I'm considering? I used existing databases of samples to represent our TTGs, our mafic gneisses, and ultramafic gneisses, in addition to getting my own brown gneiss samples and 1 mafic gneiss sample from a site called Knock-an-Sibhian, which is the largest possibly supercrustal body in the Lewisian. I've marked the sample locations by open circles in the map on the right, and a lot of them have also got bold text next to them to denote a specific locality. And Knock-an-Sibhian itself is shown in orange. And here's me collecting one of my last samples in the field from Knock-an-Sibhian. So to kick off our phase equilibrium modelling to find our maximum pressure temperature conditions, I initially focused on the mafic gneiss from Knock-an-Sibhian, which I collected from very near the location in this photo, actually. The figure here shows images of the minerals in the mafic gneiss in thin section, and the same image shown as a chemical map, which makes the different faces slightly easier to see. The mafic gneiss is interpreted to preserve a peak assemblage comprised of 2 pyroxenes, garnet, plagioclase, ilmenite, and some melt. I can then use a phase equilibria diagram that maps how the stable mineral assemblages change with pressure and temperature to work out what pressure temperature conditions were experienced by the sample. We're also going to use this technique to calculate the density of the rock. The field that contains the peak assemblage is highlighted in bold on the PT figure. Additional constraints from garnet chemistry give peak pressure temperature conditions of about 8 to 10 kilobars and 900 to 1000 degrees Celsius. This estimate is consistent with estimates of peak pressure temperature conditions from mafic gneisses across the whole central region, our region of interest, which are compiled on the right with the result from this study superimposed in grey. Another thing we can do is assess the water content that is required to stabilize the peak assemblage. The figure here shows how the stable assemblages change with water content along the x-axis and temperature along the y-axis at a fixed pressure. The peak assemblage for the mafic gneiss, again highlighted in bold, is only stable at low near anhydrous water contents, supporting the idea that the Lewisian is nearly dry at peak conditions. On the right, we just see a similar model for changing water content, this time versus pressure at a fixed temperature. So, going forward, we take the peak pressure temperature from our Knock-Ancidian mafic gneiss and mafic gneisses from across this whole region as representative of the peak conditions that all the rocks in this region experienced. As I said, we then carried out further phase equilibria modelling on the rest of our samples to work out their mineralogy and their density at these peak conditions. And the results of that modelling is summarised here. This figure shows the minerals that are stable at peak pressure temperature conditions for each sample, coloured by lithology. So TTGs are shown in blue, our brown gneisses are shown in orange, our mafic gneisses in grey, and our ultramafic gneisses in purple. So for example, we can see that if we look at olivine, our ultramafic gneisses generally contain between 40 and 80% olivine. We can summarise this information on the following pie charts. So here we are considering the average volume of each mineral in each lithology at peak conditions. The most felsic, silica-rich lithologies are shown on the left, and then we move towards more mafic and silica-poor lithologies on the right. A key outcome here is that quartz, which is shown in blue, and feldspar, which is shown in grey, are really dominant in the TTGs. And then as we move to more silica-poor conditions through the other lithologies, we see that we can become increasingly rich in pyroxene and garnet and olivine, which are shown in our reds, pinks and oranges, and then greens for our olivine. We can also calculate densities in our at peak conditions for each sample. And again, we colour these results by lithology, with the vertical lines denoting the average density for each lithology. So again, our TTGs are shown in blue, our brown gneisses in orange, our mafic gneisses in grey, and our ultramafic gneisses in purple. These averages are summarised in the table on the right. This is useful because for our model of density-driven settling, we want to know what the density contrast usually is between our TTGs and our non-TTG lithologies. These contrasts vary from 0.11 to 0.56 grams per centimetre cubed, with the larger density differences occurring with the more mafic lithologies. The evolution of our density differences over pressure temperature space can also be calculated. And on these figures, our peak pressure temperature conditions are highlighted by the grey box. So for example, here on the left, we calculate what the density difference is between our brown gneiss and our TTG over a wide range of PT conditions. And a key thing to take away here is that density differences are not generally going to exceed the value calculated for peak conditions as pressure and temperature are reduced. Okay, so we've got through the phase equilibria modelling, and we can now use the information from these previous sections to provide constraints on our model of Sagduction. To model Sagduction, we have our dense layer overlaying a less dense layer, giving a density instability. This instability develops into a solid particle falling through a viscous fluid, and this will initiate in the upper crust. The particle is comprised of one of the non-TTG lithologies, and the viscous fluid is made of TTG, which we've just sort of shown with our little schematic reminder of the TTG. We model the particle as falling through Stokes settling throughout Sagduction, as this is the fastest the particle could move. And throughout this whole process, our model is designed to give Sagduction the best chance of succeeding. Using Stokes' settling law, we're able to calculate the viscosity the TTG fluid must have to allow sagduction for a sagduction event with a specific set of parameters, such as the density difference between the particle and the fluid, the radius of the particle, the distance the particle has traveled, and the event duration. We're also able to calculate strain rate in the fluid, given the radius of our droplet and the velocity our droplet is traveling at. So having obtained a viscosity for the fluid from Stokes settling, we can then use mineral flow laws to explore what temperature is required to give this required fluid TTG viscosity. From our phase equilibria modeling, we know the TTGs are predominantly feldspar and quartz at peak conditions. So our fluid behavior is controlled by the feldspar and quartz flow laws. And from our fieldwork, petrography, and phase equilibria modeling, as we just went through, we know the depth the particle reached and the maximum temperature it experienced. We also know the density and mineralogy of the TTG fluid. So in the following model, we're going to vary the particle lithology, going through our 3 lithologies that we've considered, our brown gneiss, our mafic gneiss, and our ultramafic gneiss. We'll also vary the event duration and the particle size to explore sagduction feasibility across parameter space. To start with, I'll just go through one possible scenario of the model. So to run our model, we choose a density difference, in this case, a brown gneiss particle. So our density difference is the difference between our TTG and our brown gneiss. We choose a particle radius, in this case, a kilometer, and we set an event duration which controls our particle velocity. From Stokes settling, we get the fluid viscosity that would be required to get the particle to its observed position. That's the black vertical line on the graph. We can then use mineral flow laws to see how viscosity varies with temperature for the calculated strain rate in the fluid, and also how this varies depending on what the mineralogy is and the wetness. The different lines shown here are for quartz and feldspar, with quartz shown in pink and feldspar shown in purple. And we show wet and dry scenarios, with dry scenarios shown by a solid line and wet scenarios shown by a dashed line. The intercept between the black viscosity line and each flow law is the average temperature that would be required during sagduction to allow the event to occur. We can then do the same calculations for different body sizes and event durations. Here, we're still focusing on the brown gneiss, but that we've expanded across parameter space, with body radius increasing left to right and event duration increasing from top to bottom. We can think about how feasible these scenarios are. We want to know what temperatures and body sizes could give sagduction. So firstly, just considering this brown gneiss particle end member and a dry feldspar flow law, we can plot temperature versus body radius for the point on the graph where calculated viscosity intersects flow law viscosity, which I just demonstrate by showing how the points from the graphs on the left are going to translate to the graph on the right. So this is the temperature which is going to allow sagduction. And as you can see, we're doing this for a range of timescales and body sizes to produce the plot on the right. We can then plot these curves for each possible particle end member and for all 3 TTG relevant flow laws, noting that as the TTG are dominated by feldspar, their behavior is best represented by outcomes closer to the feldspar flow laws than quartz. That is the purple for our dry feldspar and blue for our wet feldspar on these graphs. We can add constraints based on our observations of the Lewisian to define the relevant regions in terms of temperature and body radius that we're interested in sagduction occurring. The largest possible particles in the Lewisian have radii of less than 5 kilometers, with 5 kilometers shown by the solid vertical dashed line on all these graphs. Temperature represents the average temperature throughout the event and is highly unlikely to be above 700 degrees. As such, we can see that sagduction is not particularly feasible in the Lewisian unless the lower crust is water saturated and entirely dominated by quartz. Both of these things are not thought to be the case in the Lewisian, which we saw from our earlier phase equilibria modeling, because we know the Lewisian is mainly dominated by feldspar, and is also thought to be mainly dry. So overall, we can conclude that Sagduction is unlikely to be responsible for the juxtaposition of rocks with differing densities we see today in the Archean in Scotland. And our modelling has highlighted a number of factors that are important in controlling Sagduction viability. The results figures we produce here can be widely applied to other lower crustal Archean terrains with similar lithologies and density contrasts. And the method we outline here can be applied more generally to other regions where Sagduction has been suggested. Our results broadly suggest that even in upper-crustal granite-greenstone belts, Sagduction is in fact unlikely, though further work is required to precisely constrain feasibility in these settings. Thank you very much for listening, and please do ask any questions in the chat, or feel free to get in touch with me on email or through Twitter after the talk. And hopefully this work will be coming soon to a journal near you, as it's currently in review. So thank you very much for listening.
I'm going to throw a question to Sophie. There's been a question, more of a comment put in the chat by Nick Roberts. They ask, the modelling seems more applicable to intercrustal migration of material rather than lower crust sagduction into the mantle, which are two components of the Sagduction models. So I suppose the model cannot negate the latter. And I wonder if you want to comment on that, explore that.
Yeah, so thanks, Nick. Yep, that's absolutely right. And apologies if I wasn't more clear in the introduction. I'm just focusing on the intercrustal component of the Sagduction model. And yeah, I think there is definitely some possibility for material to sagduct effectively from the lower crust into the mantle, and indeed evidence that you're seeing some diapir-like processes, potentially more of a rising diapir-like processes, which you could still kind of model with this kind of setup in modern settings in subduction zones, and there's been a bit of recent work on that. So yeah, this is very much only for the crustal component. Thanks.
Cool. And actually there's just another question come in for Sophie. So while we're on a roll, Sophie, this is from Bob Cliff. How did you arrive at your estimate for maximum average temperature, given that garnet granulite temperatures are recorded at times 200 to 300 million years apart?
Yeah, so basically that could have been spoken about for a bit longer in the talk, but I can go into it in a little more detail now. Just sort of saying the 700 to 750 figure is sort of a generalization. One way to think about it is we have a constraint on the maximum temperature reached by these rocks, which is about 950 degrees. So there's a few options in terms of a geotherm to get you 950 degrees at depth. Going from, our pretty much linear geotherm, which would give you an average temperature through the crust of, I think, just over 400 degrees. And going to the absolute extreme case of very curved geotherms, where you've got really intense temperatures throughout the whole crust. Sorry.
Oh, sorry, keep going.
Okay. But then, yeah, in the Lewisian, for example, we basically see this central region which experienced granulite conditions, which has then got two blocks on each to the north and the south, which experienced amphibolite conditions. And there is debate about whether these are all representing the same bit of crust, but potentially working on the assumption they are, you're showing that your crust experienced different temperature conditions at different depths. And we broadly think that you're at a scenario somewhere between a linear geotherm and a very curved geotherm, suggesting that potentially temperatures of around 700 to 750 degrees as an average throughout the whole crust is a reasonable upper bound. But we've also considered more specifically exactly what temperatures would be required for different particle sizes and different flow laws. So for example, when you're narrowing down into feasibility in the Lewisian, your biggest particles are those which are composite, so composed of your lighter density brown gneisses and some of your mafic gneisses. For those bodies anyway, you always need temperatures which are basically in excess of 800 to 900 degrees in all scenarios. And those are the biggest bodies. And then when you start to look at the smaller bodies, which tend to be your mafics and your ultramafics, the trade-off between body size at temperature still means you're looking at really high temperatures. So yeah, there's definitely a bit more nuance to it than just saying 700 to 750. And I am happy to discuss that further. So feel free to get in touch, but I should probably stop. Thank you.
Thank you so much, Sophie. I'm sure, hopefully that answers Bob's question. Cool. Well, we don't have any other questions in, and we're just about right on time. So I think that was wonderful. I think I will call it there and thank both of our speakers. Thank you so much, Sophie and Dan, for agreeing to give these talks and giving these wonderful talks. I hope that the audience has taken something away from them, and thank you so much for coming to support our COMET webinars, and particularly our COMET students today.